All right, so a few more seconds. I'll stop at 120. All right, A is right. Very good. All right, just quickly, I'll run through it, but it's the velocity of the ball is or the momentum of the ball is the only momentum initially, so that's 0.5 kilograms. That's the mass of the ball times its velocity of 10 meters per second is equal to the mass of White Goodman, which is 100, times the final velocity. So that's 5 over 100, which is 0.05. Is his final velocity. So a much smaller velocity than what he had before. If you watched dodgeball, I mean, the people don't really move when you hit them with a ball because it's such a small mass and such a small velocity. All right. All right. Likely, when you have a conservation of momentum problem on the test on Wednesday, which you will have a conservation of momentum problem, it'll be a two-dimensional problem, and so it's very similar to what we've been doing already, except we're just going to treat the dimensions separately. So, for example, here, we say that the initial momentum equals the final momentum, but it's also true that the x, y, and z components of all of those momenta are also equal. So the initial momentum in the x direction is equal to the final momentum in the x direction, and the same for y and z. This applies to 3 dimensions, but if we saw it, you'd only see it in 2 dimensions. All right, so let's just try an example. I have 2 particles, and I want to know, I give their velocities in vector notation there, and I want to know what is their final velocity. So there's their masses. I give the final velocity of particle number 1, and I want to know the final velocity of particle number 2. This works out exactly the same way as we did with one-dimensional problems, except we're just going to separate the I and J components. All right. We've done this before, sort of. We did this with Newton's second law. Like we said that the forces were equal to ma, but really it was the forces in the x direction, y direction, and z direction. So we're doing a similar thing here. So what we'll do is we'll say that initial momentum equals final momentum. That is that m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. So this is exactly the same as we've done so far, except now when I put these values in, I'm going to put them in vector notation. So it looks like this: 2 kilograms times v1i, which is 4i minus 1j, plus 4 times negative 1i. So those are just my initial velocities for these 2 particles here and here. And then that's going to equal m1, which was 2 kilograms, times this velocity, negative 3i minus 2j, plus m2 times v2f. And I want to find v2f. Right? And you just solve for v2f, but you keep your I and j components separate from one another. So as you propagate all this out, all these numbers out, you're going to keep these i's and j's. They don't go away. Whoa, what was that? And they stay attached to the number. Let me change the color scheme, right? Let me show you. I'm going to go to the next.
Last one, the MV2F, isn't that, don't you know M?
Oh yeah, I do know M. It was 4 kilograms, right? All right. Yeah, so V2F is the only thing that we don't know. I'll go to the next page, or you can do it there if you like. But this is going to simplify down to 8i minus 2j. Minus 4i equals negative 6i minus 4j plus 2 v2f. Was it 2 or 4?
4.
Oh, it's 4, yeah. And then you solve for V2F. So I'm just going to combine all my I and J terms. Combine that and I get 4I. And then I combine that and I get 10I over here. See, 2J plus 2J. What it is, I just brought this over here and combined it with that negative 2J. So it becomes 4 minus 2J. So 10 plus 2J equals 4 V2F. And then I divide by 4. And I get 2.5I plus 0.5J. So that second particle is going to have a velocity in that direction. Alright, we'll try one on our own in just a second. So I think you'll have it next. Alright, want to try this on your own? It's exactly the same as we've been doing. You're just keeping those I and J terms separate. And if you saw it on the test, it would be something very similar to this. Alrighty? Alright. Is that okay? Try it on your own. I'll give you a bit of a head start. Very similar, just different numbers. We'll know the final velocity of the first particle. First thing you want to do is write an expression for V2F. And it's given in words up here. an answer, anybody?
2I minus 4J.
Is that, y'all agree? 2I minus 4J? Let's check it out. That's pretty easy, right?
I get 2I.
What's that?
I get 2I.
Well, let's see. So,
When you end up getting
let me just work this out. So 2 times 3 is 6I minus 8J equals 2V1F plus 2I. And then I get, I bring the 2I over, so this is 4I minus 8J divided by 2 equals V1F. And so that's going to be 2I minus 4J. Is that what y'all said? Equals V1F. Alright, so that's the right answer. You could do this not in vector notation, but with angles and magnitudes, but I'm not going to do that. If you see a momentum problem in 2D, it'll be like this with vector notation. Nothing fancy, just two particles colliding at different angles, but given in vector notation. It's a lot easier to do when it's in vector notation. You have to go back and forth between IJ notation. Alright, is this clear, folks? Okay. Almost certain to see a question like this. So. Y'all can do it right now, that's okay. Everybody has to okay with this? You figure out the problem, Andrew?
I didn't subtract, so I added some.
Okay. Alright, let's look at a couple of different kinds of collisions. There are two types of collisions, elastic and inelastic. In elastic collisions, both energy and momentum are conserved. That means that when they collide, no energy is lost to sound or heat or deformation of the solids. You know, there aren't very many types of these. These are only objects that are only collisions that involve conservative forces, so they conserve energy. And what types of forces are conservative? What types of forces always conserve energy? Field forces, because they require no contact between the objects. And so anytime you have an elastic collision, almost certainly it's going to be, or not almost certainly, certainly it will be involving field forces, because those conserve energy. And what are some collisions that involve field forces? And y'all are all chemists. Collisions between, right, molecules or gas particles. When they come together and collide with one another, they never actually touch because they have these electric fields surrounding them, and they actually just sort of glance off of one another.
When we get kind of like that, we kind of all do that because we've never touched anything in our lives. Really, there's like less than a picometer between me and this desk. I'm not touching this desk. If you want to talk by that.
So talking about like magnets that have opposite, or would that be?
Right, yeah, so magnetic or electric forces. And then the objects, I'll show you in a video in a second, where they don't actually collide with one another. All right? Thank you, Scott. I appreciate it. All right, so a good example of this are intermolecular collisions, or collisions of gas particles. I guess every collision is intermolecular, isn't it? But in particular, gas particles in an ideal gas means a diffuse gas. But we can also approximate some collisions as elastic, and we often do this because a lot of collisions are almost elastic. So, for example, collisions of billiard balls, those are pretty darn close to elastic because the balls don't really deform at all, hardly. They emit sound, but there's so little energy that goes into sound that it's a negligible part of their energy, and they don't really heat up that much either. So billiard balls colliding, because they're so hard, are pretty good elastic collisions, and you can treat those fairly well as elastic. And then there's also not much friction, because rolling friction is very low, and so you don't lose a lot of energy in friction. All right, so elastic collisions, energy and momentum are conserved. In inelastic collisions, only momentum is conserved. Energy is not conserved. Listen, momentum is conserved in every collision that has ever occurred. So anytime you have a collision, no matter what kind of collision is, it's going to conserve momentum. Whether it's two billiard balls colliding and bouncing off one another, or if it's just running into somebody out in the hallway, you should do that. Like when you're walking through Belcher when it's so busy, run into somebody and say, hey, we just conserved momentum, and see what they say. It's like that conserve momentum too, like when they punch you in the face, yeah. So, but momentum is always conserved, no matter what type of collision. Even in like when you run into a crash test dummy, or when you run into a student walking out in the street, or if you have a car accident, that's momentum is conserved. All right, and that's what makes momentum a really powerful thing to use, because it's so applicable in just like everyday life stuff. So these are most collisions in the universe. These are all collisions in the universe. Or excuse me, not all, because some of them are elastic. But momentum is conserved in every collision that has ever been or ever will be. All right. Let's see. There's a subclass of inelastic collisions called perfectly inelastic. You don't really need to know that it's called perfectly inelastic. I won't quiz you on it. But it's just a collision where you have two particles, and after they collide, they stick together. And so they move away with the same velocity. So for example, here I have these two particles moving together, and then they move in the opposite direction. Let's see, I think I have a quick test question. So let's try that. This is different because it would work out in this way. You'd have M1 V1 initial plus M2 V2 initial equals M1 plus M2 times V final, because they both have the same velocity. It's actually quite a bit easier to work out these problems because you don't have two separate final velocity terms, you just have one final velocity terms. So the objects stick together upon colliding. So they both have the same final velocity. What's conserved in these? Momentum, right? Momentum is conserved. Energy is not conserved. M1 plus M2 VF. You want to try a problem on the next page? You could see one like this, so yeah, okay. Sure. That's momentum, not mom. That's short for momentum. In case you're wondering.
I figure.
All right, let's try this problem. Next page.
Okay.
Momentum. Mom is short for momentum. Do y'all call your mother mom or mama or something? What, Lauren? Mama? What about anybody else? Mommy? Mom? Mom? Really? I tried to get my kids to call me Pa, but they never went Pa.
That's my dad, Bernie. Just listen.
I don't know. I think that pop sounds weird.
What?
I think that pop sounds weird.
Pa? Yeah, I think it's different. Like it's Grandpa. Yeah, have him call me Grandpa.
Yeah. That sounds more like your grandpa.
Just do your work. Alright, so this is similar to the one we had before, and you could see a 2D momentum problem like this instead. It's actually a little simpler. Just try it out for practice. answer? What'd you get, Lou? Okay. Y'all agree with that?
0.67 minus 133.
All right, let's try it out. So I get 8i minus 2j minus 4i equals 6vf. And then that's 4 minus 2, 4i minus 2j over 6 for both of them, which is equal to vf. So that's right. Very good. So that's your final answer? That is correct. All right. Everybody should get these correct on the test. All right. Oh, my button was undone. It's not. You know, I came to class the other day. When I ride my bike, I have a little orange strap that I put around my leg to keep my pants leg out of my chain. And I still had that orange strap on, and nobody said anything. Who saw it and didn't say anything?
I didn't know what it was.
You saw it and you didn't say anything? Watching out for you. You saw it? You thought I was an idiot. All right.
Oh,
What?
it was just some new fad of it. You're trying.
Oh shoot, I forgot to bring these. Okay, I'm sorry, I'll bring these next time and I'll show you this little demo. It's kind of cool. I want to do one other type of problem. You might do this in PChem. I'm not sure if you go through this because in the collisions between gas particles, the fact that momentum and energy are both conserved is very useful. It allows you to actually track out the position and the momentum and the velocity of every particle for all eternity, basically, for all time. Because you have enough equations to solve for the motion after each collision. So let's just do a simple... Well, normally if you have two particles colliding, you only have one set of equations because of the conservation of momentum. But if energy is also conserved, then you're adding in another set of equations. And that allows you to solve for all the various unknowns. Yeah?
Are we talking about gas-like particles, or are we actually talking, now we're getting into quantum mechanics?
No, I'm just talking about like a classical approach to particles colliding. And in fact, I mean, in thermodynamics, they don't really consider quantum mechanics. They consider just a classical approach, momentum and energy of gas particles colliding. And then develop that into thermal physics, basically, which is, I think that's PChem 1. Is that right? Who's in PChem right now? You're in it? You already took it. Did y'all do that? All right, so let's say that we have two particles. We'll just do it in one dimension, but you can do it in two dimensions. Let's say I have a 1 kilogram particle. Obviously, this isn't a gas particle, but we're just sort of doing it for fun, because that would be a very large gas particle.
Scary.
Yeah, and it has an initial velocity
How do we know?
equal to 2 meters per second. And then I have another particle that is 2 kilograms, and it has an initial velocity equal to 0. V2 initial is equal to 0. And they collide, and they undergo an elastic collision. And because it's an elastic collision, I have both energy and momentum are conserved. Now, if I have an inelastic collision, I have to know the velocity of one of the particles to solve for the velocity of the other particle, but that's not the case here. I can solve for both of them because I have two sets of equations. I can say that the initial momentum equals the final momentum, and I can also say that the initial energy equals the final energy. Now here with the energy, we're considering them in the same plane, so they have the same potential energy, but they have different kinetic energies. All right, so I can draw up these two sets of equations. They'll look like this. I'll have M1 V1I. I'm going to leave off V2I because it's equal to 0. That's going to equal M1 V1F plus M2 V2F. And then I can also say that 1/2 M1 V1I squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. So let's see if I mark my unknowns in this. The only unknowns that I have are v1f and v2f. So I have two unknowns and I have two equations, so I can solve for those. And you know that also applies, like if I have three particles, I have three unknowns and three equations. If I have four particles, I have four equations. I have enough equations to solve for the next set of positional and velocity information for each particle. So people do this when they do these big calculations, like they'll say, I have 1 million particles, and they have 1 million equations, and then they can solve for the velocity of each of those individual particles. Not by hand, obviously. All right. So
Be a lot bigger.
the algebra here gets a little complicated. But what you want to do is solve this first equation for v1f, and then you'll sub it into the other equation. So v1f here, just solving this, is going to equal m1 v1 initial minus m2 v2 final divided by m1. And that's equal, just using the numbers that I have, that's equal to 2 minus 2 v2f. I skipped a couple of steps there. I just put in the numbers, all the numbers that I know, which is everything but v2f, and simplified it down. All right, so once I solve for v1f, I can plug that in for v1f here. So substitute v1f equals 2 minus 2 v2f into this equation, and then you just have one unknown. And it looks like this. I would have I'm just going to put in the numbers that I know. 1/2 of 1 times 2 squared equals 1/2 of 1 times 2 minus 2 v2f squared plus 1/2 of 2 v2f squared. I have one unknown there. I'm not going to solve it here, and I wouldn't expect you to solve something like that on the quiz. You just don't have enough time. And nobody would get it right either, because the algebra there are too many mistakes to be made in the algebra. But you should know that in an elastic collision, that you could follow this approach to find the velocities, the final velocities. So if you do this, if you do all the algebra, you get v1f, or excuse me, v2f equals 4/3. Actually, you get two sets of solutions, but we'll just go with that. All right. So on the test next week, as I said, I'm not going to have you solve these systems of equations because the algebra is too complicated. But you should know how to set it up. I'm not sure that I'll ask you a question like this, but I could, and it would be somewhere along the lines of I would ask you to set up these two systems, these two equations right here. But I'm not sure yet if I'll put that on the quiz. That's uncertain. But you do need to know that in elastic collisions that both energy and momentum are conserved. Y'all see the power of this? That if you have this number of equations, you can find the position and velocity of these particles. That's extremely useful, I think. It is extremely useful. It's not just me that thinks that. Like, a lot of people think that. Because it allows you to track these particles throughout space. Yeah. Yeah.
Thank you.
All right. I don't think we finished the concept test. Did we finish the concept test for this chapter? Oh, don't think so. Let's do that. We have about 10 more minutes. So I've already posted it online, actually. I did it this morning.
Wait, what did you post?
The concept test. I actually did a trimmed down version. Have we done it at all for chapter 6? Okay, well I have a shorter version online. So we've seen this? Not at all? Okay. We'll do what we can. We can come back to it on Monday. An open cart rolls along a frictionless track while it's raining. As it rolls, what happens to the speed of the cart as the rain collects into it? And the rain, you assume that it just falls directly into the cart. Remember, momentum is always conserved, and in this case, the initial and the final momentum are going to be equal. Stop at 45. Very good. It slows down. Momentum is mass times velocity. So I'm increasing the mass, and since momentum has to be constant, the velocity decreases. System of particles is known to have a total kinetic energy of 0. What can you say about the momentum? We've had a question identical to this, I think. Stop at 55. 55. Okay, remember if the kinetic energy is 0, what are the particles doing? Right, they're just standing still. They're not moving at all, and so they have no energy. So if they're not moving, then the momentum of the system is 0. Now remember, if their momentum is 0, they can either be not moving, or they can be moving in opposite directions with equal momentum, equal but opposite. But in the case of kinetic energy, which is a scalar quantity, if it's 0, that means they're not moving. Stop at 30. Okay, very good. So remember, if the momentum's 0, they're either not moving or they're moving in opposite directions with equal momentum. Stop at 30. Okay. they do not necessarily have the same kinetic energy because it's a different relationship. It's mass times velocity versus mass times velocity squared. It's a little tricky. Small car and a large truck collide head on and stick together. Which one has the larger momentum change? Remember Newton's third law. Newton's third law, what does that say about the forces involved? Stop at 45. 45. We'll just do one more, then we'll be done. Okay. C is the right answer. We want to think in terms of Newton's third law, and we're looking at momentum change, not an acceleration. Right now, the car might feel a larger acceleration. Well, actually, yeah, the car might feel a larger acceleration, but it feels the same force. So remember Newton's third law says if I have a force in this direction, I have an equal and opposite force in this direction. So when the two objects collide, they both feel the same force, just opposite directions. And since I know that F is equal to delta P over delta T, if they feel the same force in the same amount of time, which they do, they have the same change in momentum. So C is the right answer. You want to remember this relationship. It'll come up a lot in some of these questions. All right, one more question, then we'll wrap up. Two boxes, one heavier than the other, initially on rest. The same constant force acts on each one for exactly 1 second. Which box has more momentum? Yeah, this is the last one. All right. Stop in 40. Oh boy. Okay, the answer is C. And we're going back to what we had before, that F is equal to delta P over delta T. All right, so if they have the same force and the same time, they're going to have the same change in momentum. Now, one will accelerate at a greater rate, right? The lighter will accelerate, but they still have the same change in momentum. All right, so we will have the mini exam on Wednesday. I intend to give you all a longer time. I was going to give you the entire class period. Now, in semesters past, I've actually allowed the students to come in early because this is a 7:30 class. There's no class in here prior to it. Would y'all like to do that? How many of you would come at 7 if I open the doors at 7? Okay, I'm still going to make it a link. It will be longer than the previous quiz, but I'm going to make it a link that would be appropriate for an hour. So if you wish to come in at 7:30 and start, that's fine. But I will open the doors at 7. Or let's do 7:15. Is that okay? 7:15. I'll send an email out to this regard. So give me an extra 15 minutes. But that doesn't mean I'm going to make it longer than I would if it was just an hour. Okay? But what's that look? Right, y'all have a great weekend.
Yeah, you got more time, so I'll make
What is the limit of when I can arrive and start?
Well, you're done at 8:30, 8:25, 8:30. So you can get here at 8:29 that's fine.
Next week,
You too.
you have a second after. I got just some of the problems. I just want you to look them over.
Very much.